Okay, today we're going to start the new unit on counting methods. So the first method we're going to look at is the fundamental counting principle. It is similar to what we did in our first unit. So if we look back at a Venn diagram, basically what we're doing is we're trying to figure out how many of each combination there was. So for example, for the one I have below here, the number of A is 17, right? It'd be the 15 plus the 2 overlap. If I asked how many is A and B, that would be just 2. Or if I said how many combinations would be B without A, that would be 10. Or if we said how many are A or B complement, that would be everything except for A and B circles, so then in this case it would be 4. So a Venn diagram, basically what we're doing with a Venn diagram, we're figuring out how many different combinations and arrangements that we were talking about. But as you can see here, it works good if you only have 2 things. So we have A and B and the overlap, or we also did the triples where we'd have A, B, and C and all those overlaps. So those kind of situations, a Venn diagram works good. We've already done that. Everything would be fine. But there's going to be situations where there's too much data or it just doesn't seem to make sense to use a Venn diagram. So in that case, sometimes an outcome table would be good. So if I asked you, if we roll 2 dice, how many 7 combinations are there? So because we got 2 dice, there's 6 numbers on each side, we get a whole bunch of different combinations. So sometimes a little table would be best if you have your 1 dice going one way and you have your other dice going the other way, and then we just basically make a table showing all of the different combinations. So if we rolled a 1 and a 1, that would give us a 2, a 2 and a 1 would give us a 3, 3 and 1 would give you 4, and so on. So we could basically fill out the table. So it would give us every possible combination of a dice roll. You can see it just follows a pattern here all the way across. So in this case, a Venn diagram wouldn't work because we'd have way too many circles and it'd be too tough to figure out all the different overlaps. So for this one then, now once you have your table filled out, it's pretty easy to count up all the different combinations. So if I said back to the question where I said how many different rolls could you get a 7, so number of 7s. So you can see here the 7s are all those middle ones, so we get 6. There's 6 different ways to roll a 7. Okay, if I said what's the number of rolls that are bigger than 10? So in this case, which ones are bigger than 10? Well, just those 11s and 12s, so that would be 3. Okay, what's the number of ways we could roll a 6 or a 4? So in this case, you'd have all your 6s. So we got 1, 2, 3, 4, 5 6s and 3 4s. Remember, or means plus, so 5 6s and 3 4s would give us 5 plus 3 is 8. Okay, let's do one more. How many ways could we roll a even number and less than 6? So how many even numbers are there less than 6? Well, we got the 3 4s that we already looked at. Right? 3 4s plus the 1 2 would give you 4. Okay, so an outcome table then, a summary, is it's a good way to kind of compare two events that have lots of different choices. So some situations it'll work good, other situations not so much. So in terms of like dice, it's a pretty good scenario. Another way we could do these would be to look at a tree diagram. So a tree diagram sort of works sort of the same as an outcome table, but it's better when you have multiple choices. So let's suppose we were going to look at to go buy a new car. So let's suppose we decided we're going to buy a truck, and we're going to go buy a new truck, and we're going to look at either buying a Dodge, a Chev, or a Ford. So we have 3 choices for a truck. Okay, so out of the 3 choices of trucks, then let's suppose we're going to decide, do we want to get a 4x4, a short box, or actually let's change that. Let's say we're going to get we're going to do red, blue, or green. So because we got those three choices, we would get those three for each of the kinds of truck that we'd get. And then let's suppose for each of those, we're going to decide on a four-wheel drive or a two-wheel drive. So then for each of those choices, we'd end up with the four and the two-wheel choice for each. So you get the idea. So we end up getting a whole bunch of choices. Let me just make those a little bit better. So we'd have a 4 and 2 for each of those. And I'm running out of room, but that's, you get the idea. So that means then in any of these combinations, if that was our only limitations, you can kind of see we have a whole bunch of different options. We got a Ford, blue, and a 4x4 would be one. We have another one that would be Dodge, green, and a two-wheel drive, and so on. So you can see basically after all these you would get the whole last column would be all of your choices. So we have 1, 2, 3, 4, 5, 6. We have 6 for each make. So you'd have 6, 12. So we'd have 18 different combinations of the three trucks, the three colors, the three trucks, the three colors, and the four-wheel drive or two-wheel drive. So tree diagrams, sometimes they work pretty good, other than they're sort of like an outcome table, except they work good for when you have 3 or 4 or 5 choices. But I don't really like them too much because it takes you quite a bit of time to draw them out. So the fundamental counting principle basically deals with a lot of this stuff, but it's an easier and quicker way to do it. So if we go back to the truck one, you see we had 3 choices for trucks, then we had 3 choices for colors, and then 2 choices for the last one. So all we'd have to do is 3 for the first choice, times 3 for the second choice, times 2 for the last choice, and that gives us the 18. So if we go back to the tree diagram, you can see we get the exact same thing, but we just have 3 for the first choice, 3 for the second, and 2. So if we multiply all those together, that'll give you the exact same total that we were doing. So fundamental counting principle, you basically just multiply each number of the choices all the way through the process. So if I said we had, actually let's look at a map kind of question. So let's suppose we're going to go from point A to point C and we have to go through point B. So this could be like a flight, you got to fly from Edmonton to Calgary, but there's 3 or 4 different flights that you could take throughout the day. And then we're going to go from Calgary to Vancouver, and let's suppose there's 3 flights that you could take for that one. So then the choice would be how many different flight arrangements could you make. So you'd have 4 choices for the first flight, 3 choices for the second flight, so that would give you 12 different combinations to get from A to C if you have to fly through B. Okay, so those kind of questions are pretty good. Another one like that that's you got to be a little bit more careful about would be, let's suppose you go from A to B1, and then from there you go to C. So let's suppose it looks something like that. But then the other option is we could fly through a different city. Let's suppose we go to B2 instead. And then from there we can go 1 flight to get to C. So if this case you do the same thing, but you just got to do each leg separately. So we got 2 choices to go from A to B1. We have 3 choices from B1 to C. So if we just do the top part, we'd have 2 times 3, which is 6. And if we do the bottom part separately, we got 3 and 1. So 3 times 1 equals 3. Because we can go one way or the other, or it would be plus. So that would give us a total answer of 9. Okay, let's look at a couple more fundamental counting questions that you'd be expected to be able to do. So let's suppose we have the word Leduc. We got 5 different letters in the word Leduc. So let's imagine these were on like algebra Scrabble tiles or pieces of paper or something, and you're going to reach in and randomly pick out a letter. So the question would be, how many different ways could you arrange those 5 letters? So using the fundamental counting, we'd have 5 choices for the first letter. Then once that one's gone, we'd only have 4 left. And once that one's gone, we only have 3 left. Once that one's gone, we'd have 2, and then 1 left over at the end. So you can see we just basically multiply each number of choices as you go. So in this case, that would work out to 120, I think it is. Yeah. So we'd have 120 different ways to rearrange the letters in Leduc. Okay, so let's try a different case. So we'll stick with the word Leduc, but now how many different ways could you rearrange the word Leduc if L had to be first? So we have L as our first letter, and then the other 4 letters could go in any order. So in this case, you'd have one choice for the L, because there's only one L. Then you'd have 4, 3, 2, 1 after that. So you can kind of see that we can still use the fundamental counting if there's special restrictions. So in that case, we'd only have 60 letters. Oops, no, I messed up. 4 times 3 is 12, times 2 would be 24. So we'd have 24 different combinations of the word Leduc if L is first and the E, D, U, and C can be rearranged in any other order. Okay, let's try one more. So what would happen if we do, let's do Kalmar. So now in this case, the problem is we get 2 different A's. So if we tried to do, if I said how many different ways could you rearrange Kalmar, we have 6 different letters. So we'd have 6 times 5 times 4 times 3 times 2 times 1. So that gives us 720. But because we have 2 A's, we're going to get a repeat of words. So if the A's would trade spots, so we'd have 2 different ways to spell Kalmar, and the A's could be switched, but it'd still be the same arrangement. Or, let's suppose we got this for a choice. Or if I had the A's the other way around, right? So let me just change colors here. So if that second A was flipped, it's still the exact same word. So that's why we have to divide by 2, because we'd have 2 different A's to worry about. So it'll still work for repeats, but it's a little bit more complicated, and that's why for these kind of questions we're probably going to use a different method. So fundamental counting works good if you just have sort of a certain number of choices for each one, and if there's repeats and things like that, then it becomes a little bit more difficult. So we'll stop there and we'll look at factorial next.